Alright, so I wanted to talk with you briefly about how we can use calorimeters to determine heats of reactions. Up to this point, all we've really looked at is putting something hot with something cold and looking at the heat exchange between the two, but generally it's far more interesting if we perform this kind of operation with a reaction, because there's a lot of information that we can extract about a reaction by doing this. There's two types of this. One type is going to involve burning things, and one type is just going to involve reactions that happen in solution without actually causing fire. So I'm going to start with the one that doesn't actually induce any kind of fire, so non-combustion type reaction. Our example problem here talks about putting some salt. Doesn't really matter what the salt is for our informational purposes. I've given it as a generic salt, MX2, that has a molar mass of 50 grams per mole. That's given right down here. And I'm going to put 5 grams of that salt into 150 grams of water in a calorimeter that has an initial temperature of 25 that during the course of this reaction, which we'll see right here, during the course of this reaction, it releases some heat, and so MX2 gets converted into M2 plus and 2X minus. You might think of this as like CaCl2 becoming Ca and 2Cl minus, and this is just a generic example of something in that vein. Now, what's important to note here is that we ask this to be recorded in kilojoules per mole of MX2, so that's going to be something that's kind of new for the processes we've been working with, so it's one of the reasons I want to walk through this with you. Other important thing to note before we get started, because this solution is dilute, the C for the solution is pretty much the same as water. It might vary slightly, but for the level and type of problem that we're working with, we're going to consider that they're basically the same thing. Okay, so just like any other calorimeter problem that we've worked with, this system should follow the first law of thermodynamics, so that part is not new, which all that really means is that Q system equals negative Q surroundings, just like it did in any other calorimetry problem. We're just going to have to make that fit into the mold that we want. So here's what we do with something like this. We generally refer to the reaction here as the system, and we refer to the calorimeter that we're working inside of as the surroundings. Okay, so what that basically does for us is lets us translate this equation into something like this. Q for the system becomes delta H for the reaction. Now, I'm allowed to do that so long as the pressure's constant. So since we're doing this in a lab where we have controlled conditions, we get to assume constant pressure. Alright, so that's going to allow me to have enthalpy come in and take the place of Q. Now, on the other side of this reaction, for the calorimeter, we still have to do a calculation. Basically, what's different about this and the other calorimetry problems you've done is this time we don't have to do as much math. This side just gets called delta H for the reaction. The other side is the negative Cm delta T of the calorimeter that we've been working with all this time. And so in this case, C for the calorimeter is C for the solution, which we said is not going to be appreciably different, so 4.18 joules per gram degree Celsius. The mass is going to be a little different than what we've done in the past. Because I'm going to put this stuff, even though it's the system, into the calorimeter, it's going to increase the mass of the water inside the calorimeter because it's going to become a solution. And so I can't physically separate the two once the reaction starts. And so when I look at the mass of this reaction or mass of the calorimeter, I have to then include the 5 grams of salt in with it. So we'll be taking this and this together to make the mass of the solution that's gaining temperature. Alright, so 150.0 grams. And, oops, sorry, I said to do that and then I didn't do it. Sorry, 150 for one and 5 for the other makes me have 155 grams. And then the temperature change is just like we've always done. T final minus T initial looks like 4.9 degrees Celsius. Okay, so delta H for this reaction, just to find the heat, basically, is pretty simple. 4.18 times 155 times 4.9, that is negative 3170 joules. Now, I left it with 3 significant digits. We probably should have only had 2, but for what we're doing, that's okay. However, that's not how this asked me to report it. If you look back up here, we asked for it in kilojoules per mole of MX2. That's not really a problem. We know how much MX2 we had. We know the molar mass of MX2. It's just a little dimensional analysis on my part. So to accurately present this information in the way it was requested, delta H for this reaction is going to be negative 3170 joules for every 5.00 grams of MX2. But I have requested that you tell it to me with kilojoules on top, and instead of grams, I have asked for moles on bottom. And so I just need to supply the required dimensional analysis steps to make this happen. I need to convert kilojoules to joules, so 1 kilojoule is worth 1,000 joules. And I need to convert grams to moles, and we're talking about MX2. And thankfully, we were given the molar mass of MX2. It takes 50 grams of MX2 to make a mole. And so then I just run through my dimensional analysis. Joules cancel, grams of MX2 cancel, and I'm left with kilojoules per mole of MX2, just like I asked for. So basically 50 divided by 5 is 10, so we've got 10 over 1,000. Well, 10 divided by 1,000 basically is like dividing by 100. So instead of having negative 3170, we have negative 31.7. We're going to drop that extraneous 0 because it wasn't really significant. It was just placeholding up here. So we've got negative 31.7 kilojoules per mole of MX2. Doesn't change the value. Here we reported it for 1/10 of a mole. We're just reporting it for a whole mole, so we've just scaled it up. Okay, the other type of problem that you'll encounter on your homework, and most likely in a lab situation when we come back from spring break, is how to use this type of information to work with a aluminum can type calorimeter. Normally we talked about in class how when you do combustion analysis you roll with a bomb calorimeter. Unfortunately those are expensive and complicated, and so we don't have access to those, and so we can substitute in their place an aluminum can calorimeter. And the reason we swap in aluminum in the place of styrofoam is because styrofoam itself is combustible. We don't want to burn up our calorimeter. And so we take our water and we place it in aluminum, which won't burn. The issue with that is that styrofoam was really good at insulating and didn't absorb a lot of heat. The aluminum can, on the other hand, is going to interact. Whatever temperature the water reaches, the aluminum is going to take some of that energy or give some of its energy to reach the same temperatures if it's holding that water. So we'll kind of work through an example and show you how that works. We're going to be determining the heat of combustion, and by that, since we're doing this in a room with fairly constant pressure and we're not doing it in a bomb, we're going to say this is delta H of combustion. We're going to lose some heat energy to work, but that's okay. We're just interested in the heat transfer with a calorimeter anyway. So we want to report this again in kilojoules per mole, but this time it's kilojoules per mole of CH3OH, which is methanol. My calorimeter has 250 grams of water. We're not going to be adding any mass to this because our ethanol is going to be outside of the water. We're just going to be transferring the heat with a direct flame. That water has an initial temperature of 20 degrees Celsius, and it reaches a maximum temperature of 32.5. So here's the deal with this, though. Like we said just a second ago, this time instead of a styrofoam cup, we've got an aluminum can, and inside this can is our water. Well, like we said, the aluminum will also accept and give heat. And so that aluminum can has a mass of 45 degrees Celsius. So calorimeter still means we've got a first law problem. And this first law problem is operating on this reaction. It's a combustion reaction, which says that negative Q system still equals Q surroundings, or however you want to tag the negative. And it's still, for the system, delta H, only instead of the generic reaction, we're going to call it combustion this time, still equals negative Cm delta T for the calorimeter. But this time, we also have involved in this the aluminum can, and so I've got two Cm delta T's here because the aluminum can is going to be involved in this as well. So it's the negative of those two things together. Okay, so delta H combustion here is going to be negative C for the water, which is 4.18 joules per gram degree Celsius. Mass of the water is 250, and delta T for the water is 12.5. Okay, so along with this, we're going to have C for the aluminum, which they gave me right here, 0.900 joules per gram degree Celsius. It's a 45 gram can, and it also does 12.5 degrees Celsius temperature change, which shouldn't be shocking. It starts out at the same temperature as the water because the water is in the can, and it ends at the same temperature of the water because the water is in the can. So not a crazy idea here. Okay, so delta H for combustion then just requires the calculation of these numbers, so I'm going to do that real quick. 4.18 times 250 times 12.5, and I'm going to add to that 0.9 times 45 times 12.5. That comes out to negative 13,600 with applying some significant figures here, joules, or I'm going to go ahead and call this negative 13.6 kilojoules. Okay, so that only difference here was that we had this and this as opposed to one thing before. Now they still want this in kilojoules per mole like they did before, so we're going to run our dimensional analysis and say that delta H of combustion is negative 13.6 kilojoules for every, what did I say, 5 grams of methanol that we used. And methanol has a molar mass of 12 for carbon and 4 for the hydrogens at 16, and then another 16 for the oxygen. That's 32 grams in a mole. And so the molar enthalpy of this then is 13.6 kilojoules times 32 divided by 5 in order to get the moles. It should be 87.0, negative 87.0 kilojoules per mole of CH3OH. Now, trust me, that's not even remotely close to the truth. This was totally just a conceptual idea. Methanol actually produces much more energy per mole than this. But the general idea is that when you have an aluminum can calorimeter or some other type of calorimeter that's not a pure bomb that's fully insulated, you basically have to account for the heat that goes into the other parts of the calorimeter that absorb heat. It's best if you can actually have a bomb calorimeter and you can combine the energy exchange of these two into one term all the time, but it's not always possible to do that, and so this is kind of our Gen Chem 1 hack for that. So just work with these, use these examples as you feel they're needed for your homework and for your labs, and hopefully this will answer some of the questions that you have.